Welcome everyone to the CPPC seminar. Our today's speaker is André Gouvêa from Northwestern University. André is an expert in neutrino physics and made several important contributions there. So one thing which I know is kind of those classification of those delta L equals 2 operators, which I used a lot. But today he will be telling us about Majorana versus Dirac beyond neutrinoless double beta decay. So please, André.
Okay, so I'm going to get started. So thank you for the invitation. Let me know if you can't hear me well, and I will try to point with my little arrow here. You should let me know if that's also not working. So I'm going to get started. My job is to tell you something about distinguishing Majorana from Dirac neutrinos, concentrating on one question that people often ask, which is when you hear about distinguishing Majorana from Dirac neutrinos, you often hear about neutrinoless double beta decay. And invariably, the question people like to ask is, can't we do this in a different way? And I'm going to discuss that the answer is probably no, but nonetheless, I want to give you some hints as to what kinds of things you want to be thinking about if you want to tell Dirac from Majorana neutrinos. I do want to say that this is aimed at I would say, relatively broad audience, so hopefully that's okay. And if you happen to be an expert, I may not say anything that you haven't heard before. Okay, so let me get started. Just for people who don't know, that's one question people ask. This picture here on the cover is a commemorative stamp celebrating 60 years of Dubna. And it does have a double beta decay in this particular Czech stamp. Okay, so let me change slides. So first of all, the question I want to try to talk about is answering whether neutrinos are Dirac or Majorana fermions. I will quickly try to give you a flavor of what that question means. And it basically has to do with the fact that now we know that the neutrinos have non-zero masses. We can ask the question about how many degrees of freedom it takes to describe a neutrino. And I want to quickly remind you of the fact that if you have an electron, because of everything we've learned from relativistic quantum field theory, electrons require 4 degrees of freedom. And we can label them according to their spin or according to their helicity. So for example, we know that there are left-handed helicity electrons. And because left-handed helicity electrons exist, I can perform a CPT transformation. And the object that's associated to this transformation is what we call a right-handed helicity positron. So the fact that one of these states exists implies the existence of the other state. Now, there's an interesting thing, which is if the electron has non-zero mass, if you ever saw a left-handed helicity electron, the fact that the mass of the electron is not zero allows you to conclude that there must be a right-handed helicity electron as well. And there are lots of simple ways of thinking about why that's a true statement. Probably the simplest one is that if the electron has a non-zero mass, you can go to the rest frame of the electron. And if I tell you that the electron is a spin-a-half particle, you know that a spin-a-half particle at rest has 2 independent degrees of freedom that we sometimes refer to as spin-up and spin-down. In helicity language, those things look like a left-handed helicity object and a right-handed helicity object. And of course, you know, the CPT theorem tells you that if you have a right-handed electron, there must also be a left-handed positron. So if you count degrees of freedom, the electron tells you that there are 4 different degrees of freedom associated to this particle. We can now do the same game with neutrinos, and we know that, let's say, left-handed neutrinos exist. Again, by the CPT theorem, if a left-handed neutrino exists, there must be a right-handed object that we oftentimes would associate with the antiparticle of the neutrino. And that's the object that's related to the left-handed neutrino by a CPT transformation. Now, just like the electron, because the neutrino has a mass, I can go, for example, to the neutrino's rest frame. And of course, a spin-a-half particle at rest has 2 independent degrees of freedom. So again, just like the electron, you have 2 states that are related by this CPT transformation. And you also have 2 states that, if you want, that are related by Lorentz transformations. Now, with the electron, we were very sure that the number of independent states was 4 because of charge. So for example, we know that the CPT partner of the left-handed electron is a right-handed positron, and we know that the Lorentz partner of the left-handed electron is a right-handed electron, and of course, a right-handed electron and a right-handed positron are for sure different particles. In the case of neutrinos, you can ask the question if the Lorentz partner of the left-handed neutrino is the same as the CPT partner of the left-handed neutrino. If the answer is yes, then the neutrino is what's called a Majorana fermion. That's the thing that's at the bottom here. And if that's the case, then the number of degrees of freedom that describes a neutrino is actually two. There's a left-handed one and there's a right-handed one. We often abuse language and we say that one is the left-handed neutrino and the other one we call an antineutrino, but that's just the name that we give to these two independent states. Now, it is possible that just like the electron, the Lorentz partner of the left-handed electron is different from the CPT partner of the left-handed electron. If that's the case, there's a right-handed neutrino and a right-handed antineutrino, and these are two different states, and the number of degrees of freedom that it takes to describe a neutrino is 4. Okay, so that's a long discussion about what it means to be a Majorana fermion versus a Dirac fermion. And one picture you have in mind is that a Dirac fermion has 4 degrees of freedom, a Majorana fermion only has 2. Now you can ask, how come we don't know the answer to that? Because 2 and 4 are very different numbers. And the reason turns out to be easy to understand is that neutrino masses are very small. And what happens is, for this story that I was telling you before to make sense, to be a meaningful story, the neutrino has to have a non-zero mass. If the neutrino mass is 0, you can't distinguish a Dirac massless fermion from a Dirac Majorana fermion. It's not really a question that you can ask because a massless fermion is happy to exist always with only 2 degrees of freedom. It doesn't matter if it's charged or not charged or whatever, but massless fermions are very happy to exist with only 2 degrees of freedom. There might be lots of them, but they don't have to be related to one another. So saying this in a different way, the reason we don't know the answer to why the neutrinos Majorana and Dirac is because we can't ask the question if the neutrino mass were 0. So what this means is, if you can come up with some observable that can distinguish between Dirac neutrinos and Majorana neutrinos, the answer that is encoded in that observable has to go away once the neutrino mass vanishes. That means that whatever physics process you come up with, it will have some amplitude that has to vanish when the neutrino mass goes to 0, which means that the amplitude will be proportional to the neutrino mass in units of whatever energy scale is in your problem. And it turns out that the neutrino mass is very small. And because the neutrino mass is very small, it means that observables that you can construct will have a very, very tiny rate. Now, as most people will have heard, the vanilla way of understanding whether the neutrinos are Majorana or Dirac is to look for lepton number violation. The reason is easy to understand. If the neutrinos are Majorana fermion, the thing that we call the right-handed neutrino and the right-handed antineutrino are the same particle. And normally, what distinguishes a right-hand or a neutrino from an antineutrino is a quantum number that we call lepton number. And because we want to equate, the left-handed neutrino with the left-handed antineutrino and the right-handed antineutrino with the right-handed neutrino, this concept of lepton number can't be well defined because I have equal and opposite lepton number assigned to the same state. So the way that we normally look for this is to look for lepton number violation. Let me explain a little bit how this works, just to drive the message in as deeply as I can. And let's do a Gedanken experiment. And the idea is, imagine I have a scattering process where I produce a neutrino. Let's say an electron comes in, hits something, and a neutrino comes out plus something else. Now, this is a charge current weak interaction. And because it's a charge current weak interaction, I can pick a reference frame where the neutrino that I produce in this process is going to be a mostly left-handed helicity object. But and this is because the charge current weak interaction is purely chiral. It's purely left chiral, which means it only talks to the left chiral field. And the left chiral field for a very, very light particle is very good at producing left-handed helicity particles. And it has a really tiny probability of producing a right-handed helicity particle. So that means when I have a process that looks like this, the state produces this thing that's in green here. So left-handed helicity object with a very tiny component proportional to m over e, which has right-handed helicity. Now imagine that I go on and I try to detect this neutrino. When I detect this neutrino, it has to make a choice. It will either be measured as the left-handed helicity thing, or it will be measured as the right-handed helicity thing. Now, the left-handed helicity thing speaks mostly to the left chiral current, and that has the ability of producing electrons. The right-handed helicity object actually has two choices. If the neutrino is a Dirac fermion, a right-handed chiral neutrino has no interactions. So that means that this object would have a really hard time hitting anything. On the other hand, if the neutrino is a Majorana fermion, this right-handed helicity object is the same as the right-handed antineutrino, which participates also in the weak interactions, but it produces positrons. So the end of the story is, if the neutrino is a Majorana fermion, I can start out with an electron in the initial state, produce a neutrino, and have this neutrino hit something, behave like a right-handed helicity object, which has a non-zero probability of producing a positron. So that's a possible thing that can occur. This violates lepton number because I started out with one electron in the initial state, and I ended up with a positron in the final state. And the probability for this to happen is proportional to this m over e factor here squared. And this turns out to be a very, very tiny number. That's what makes this kind of search very difficult. The usual way to look for this is to look for neutrinoless double beta decay. That's the thing I'm not going to be talking about very much, but I do want to emphasize that double beta decay is kind of like the process I was describing before, but turned on its side. You basically start out with a state that has no electrons in it, and you end up with a state with 2 electrons. You violate lepton number by 2 units, and assuming that this diagram is the dominant contribution to neutrinoless double beta decay, the probability for this to happen, or the amplitude, is proportional to some linear combination of neutrino masses. There's a lot of activity in searches for neutrinoless double beta decay. So this is a plot from the Campbell and Zen experiment. They're looking for neutrinoless double beta decay. People can ask me about it later. And people tend to quantify their results by saying that there's some effective neutrino mass that has to be less than something if the neutrinos are Majorana fermions. And right now, this Campbell and Zen result rules out values of this effective mass somewhere inside of this red band. And there's a big uncertainty here because of nuclear matrix elements that I'm not going to talk about. But neutrinoless double beta decay is a very exciting field because there are several big experiments that are taking data. There are several bigger experiments that are being planned. And there's a whole bunch of other kinds of experiments, including dark matter search experiments, that are starting to become interesting places for you to consider looking for neutrinoless double beta decay. So there's a big industry, and we're hoping to make a lot of progress. And in particular, for people who are paying attention to this sort of field, I would say the goal of this kind of activity is to be able to either discover neutrinoless double beta decay if the neutrinos are Majorana fermions and if the neutrino mass ordering is inverted, or to rule out the inverted ordering if the neutrinos happen to be Majorana fermions. So it's very exciting, and the goal is to, if you stare at this picture here, it has the expectations for what this observable should be, but it's to kind of get to the bottom of this green region over here. And if you don't know what I'm talking about, this probably didn't make a lot of sense. Okay, so My job in the next half an hour or so is to try to tell you what else is there if you want to distinguish Majorana neutrinos from Dirac neutrinos. And there are two ways of asking this question. One, of course, is that I mentioned that looking for lepton number violation is a great way to tell if the neutrinos are Majorana or Dirac. So you're allowed to ask if there are other ways to look for lepton number violation that are not neutrinoless double beta decay. That's one good question. Another good question is, let's forget about lepton number violation. Can I do something else to distinguish Majorana from Dirac fermions? So I want to talk about those two things. I'll talk about the second thing more, but just very briefly, you can ask yourself, can I look for lepton number violation in different ways? And how do I do that? The short answer is there are lots and lots of different ways of looking for lepton number violation. The problem is before you would decide that you want to invest a lot of time doing this, you need to worry about two things. One thing you need to worry about is constraints for neutrinoless double beta decay are very, very, very strong. There's no other probe, naively, that can compete with neutrinoless double beta decay. So that's one big concern. And there are lots of ways of circumventing that. One very easy way is that neutrinoless double beta decay is very sensitive to the electron flavor of things. So if somehow you can hide the lepton number violation away from the electron flavor, you might be able to say that the rate for neutrinoless double beta decay is very small because of flavor physics, which means that you have to look for lepton number violations somewhere else where the flavors are not just the electron flavor. So if you're happy with solving the problem this way, there's another problem, which I'm not going to dwell on very much, which is neutrino masses are very small. And it turns out that if the neutrinos are Majorana fermions, that physics that contributes to neutrino masses also will find a way to contribute to lepton number violating processes. And it is often the case, but not always, where the naive neutrino mass bounds that you impose on the new physics will make the rates for neutrinoless double beta decay or lepton number violating processes outside of neutrinoless double beta decay ridiculously small. This is also not a mathematical theorem, and there are lots of interesting, exciting ways to circumvent these very, very strong tiny neutrino masses and other processes that look for lepton number violation. And that's not what I'm going to talk about in this talk. I do want to show you, however, that if you go to the PDG or to the website with the PDG, here's a page of all the different things that people are looking for that have to do with lepton number violation. Neutrinoless double beta decay is on this list. So it's the thing that's highlighted here in red. If you actually go to the PDG, this is not the whole story. There's a second page, which has a bunch of other processes. And most of these processes are meson decay processes. There are going to be variations on K plus to pi minus, mu plus, for example. What I do want to highlight very briefly is that if you throw away neutrinoless double beta decay, the second best search or the second best place to look for lepton number violation is probably mu minus to E plus conversion. This is a process that looks like mu to E conversion. That's when a nucleus captures a muon, the muon interacts with the nucleus and converts into an electron. So that's what people call mu to E conversion. Mu minus to E plus conversion is a similar process, but except that the muon gets captured and a positron comes out violating lepton number by 2 units. These bounds can be very strong because they're also, you can look for these things in the same place where you look for mu to E conversion. And it's exciting to pay attention to this because there are 2 new efforts, one in the US, one in Japan, that are invested in improving our sensitivity to mu to E conversion. And at least one of them, the one in the US, can improve on the mu minus 3 plus conversion bound, hopefully by a couple of orders of magnitude. So it's something, it's a good space to watch. Okay, so let me turn to the more less familiar question, hopefully, which is, so let's forget about lepton number violation for now. And the question is a simple question. If I have a Majorana neutrino and a Dirac neutrino, is there other physics that I can talk about where I get different answers depending on whether the neutrinos are Majorana or Dirac? The answer turns out to be yes, in quotes. So you can construct an observable that does not really speak to lepton number violation directly, but can distinguish Majorana from Dirac neutrinos. And these are weird observables because they're not as a smoking gun as lepton number violation. And I think it's always possible to fool yourself by making the Majorana neutrino do the same thing that the Dirac neutrino does by adding some new physics. So I'm going to put that concern aside, and I will assume that there's no other new physics that could be making my life hard, and that I only have, in quotes, standard model physics plus massive neutrinos. So let's go back to understanding why answering this question is really hard. And it comes down to this slide that I showed you in the beginning, is that neutrinos are produced by the weak interactions. All of your neutrino beams turn out to be very, very heavily polarized. And the probability of seeing that the neutrino is a Majorana fermion versus a Dirac fermion somehow vanishes when the neutrino mass goes to zero. So again, the problem is that the neutrino masses are too small. Of course, saying that something is very small is an ill-defined concept, especially if the something has units. So you have to say that the neutrino masses are very small relative to, let's say, the typical momentum transfers of the physics process that you're interested in. So a different way of saying what the problem is all of the experiments that we do are experiments with ultra-relativistic neutrinos. And a good way of reminding ourselves of that is we have never seen the effect of a non-zero neutrino mass in any experiment, except for oscillation experiments. So that means that any experiment that you can think of is such that the neutrinos can always be treated as being perfectly massless. And that means that in any of these experiments, you're not allowed to answer if the neutrino is Majorana or Dirac. So the problem is, from an experimental point of view, that we're always working with neutrinos that have gigantic energies relative to their mass. So how do we get around this? And the answer is naively very simple. We can find some neutrinos that are not super energetic. So we can ask questions, what if I do an experiment where the neutrino energy is not much, much larger than the neutrino mass? So if we did that, we wouldn't have this problem that the distinction between Dirac and Majorana neutrinos is kind of hidden because M over E is very small, and that seems to be a good place to go. Now, why don't we ever talk about this? We don't talk about this for a really, really simple, good reason. Actually, there are two reasons. One is it's very difficult to find a source that only emits ultra low energy neutrinos. All of our sources, even those that have a big spectrum, they might contain some very, very low energy neutrinos, but they also contain a whole bunch of much, much higher energy neutrinos, and that means it's not a very clean source. The reason for why you worry about not having a very clean source is that, of course, neutrinos are always measured by the weak interactions. And it turns out that as you go to low energies, in the case of neutrinos, even pretty high energies are low, the cross-section grows with the energy to some power. So that means that as the energy gets smaller and smaller, your cross-section is getting smaller and smaller, which means that whatever observable you've constructed, it won't give you a lot of statistics. Okay, so that's the problem. And it turns out that this is a really big problem. I don't want to oversell the solution, but from a more academic point of view, I do want to try to convince you that if we could measure these very low energy neutrinos, distinguishing whether they're Majorana or Dirac would be completely trivial. That would not be the problem at all. Okay, so that's what I want to try to talk about, and I'll give you some examples. So if you wanted to study non-relativistic neutrinos, what kind of choices do you have? And I've highlighted 3 different choices. One is you can look for a place where there are a whole bunch of very, very low energy neutrinos. And a good place for that is the cosmic neutrino background. Another thing you can do is I told you that coming up with a source of very low energy neutrinos is very hard, but we could start out with a non-neutrino source that's low energy, and maybe we can produce the neutrinos that have a very low energy. So we can talk about having low energy neutrinos as a final state of my detection and not having the neutrinos be in the initial state. And then the third possibility, it turns out, is we can look at neutrinos as decaying particles. And the important point here is that if you have a particle that decays, it clearly has a mass, and the mass will be very visible. And I'll try to make that more clear later on. Okay, so I will briefly talk about the cosmic neutrino background. So this is work that was pointed out already quite a long time ago. I think this is a nice paper that explains why the cosmic neutrino background is potentially a great place to distinguish Dirac from Majorana neutrinos. So again, we know there's a cosmic neutrino background. It's characterized by a temperature that's of order 10 to the minus 4 electron volts. That's less than the masses of at least 2 of those neutrinos. That means that at least 2 of the neutrino mass eigenstates from the cosmic neutrino background today are on average not relativistic. So good, so we have a source of non-relativistic neutrinos. And let's say for the sake of argument that I'm going to measure these neutrinos by some charge current process. And let's say for the sake of argument that the charge current process will be this one here in bright red, which I'm going to refer to as induced beta decay. So this is a process where a neutrino comes in, hits a nucleus, and an electron comes out. So if I'm detecting the cosmic neutrino background in this way, the difference between a Dirac cosmic neutrino background and a Majorana cosmic neutrino background is huge. So let me tell you why that is, and that will be just a story. So if I want to describe the neutrinos in the cosmic neutrino background, I can use language where I say that half of those neutrinos are going to be of left-handed helicity. And by the way, even though they're non-relativistic, they maintain their helicity as they cool down because they don't interact with anybody since they were ultra-relativistically. So there's half of them are approximately half of them are left-handed, approximately half of them are right-handed. Okay? Now, normally we refer to the left-handed component as neutrinos and the right-handed component as antineutrinos. And I will use that language independent of whether the neutrinos are Majorana or Dirac, because I will remind you of what the neutrinos can do and the antineutrinos can do, depending if the neutrinos are Majorana or Dirac. Now, the key point is a left-handed neutrino will talk to a left chiral field in the Lagrangian, and the right helicity state will talk to the right chiral field in the Lagrangian. Okay, so that'll be again, we talked about this a little bit before. So if the neutrinos are the Dirac fermion, I actually forgot the important part. Now, so erase the last sentence I said because that was wrong. So here we are in the opposite regime, which is the state is not relativistic. So imagine you have a neutrino at rest with a spin pointing somewhere. So it's a polarized neutrino. When it interacts via the weak interactions, half of the time it will talk to a left chiral field, and the other half of the time it'll talk to the right chiral field. That's what happens with a neutrino at rest. That's actually what happens with any fermion at rest. If you try to speak to a current, it'll either be a left chiral current or a right chiral current. So that means if the neutrinos are Dirac, and I have my neutrinos, and that object is going to try to talk to my nucleus to undergo this reaction over here, when it wants to talk to the nucleus, it'll either behave like a left chiral current, and then the reaction will go, or it will behave like a right chiral current, and the right chiral current doesn't participate in the weak interactions, so nothing happens. Okay, so that's what happens with the neutrino component of the cosmic neutrino background if the neutrinos are Dirac. And then there are the antineutrinos. The antineutrinos, again, they will half of the time interact using a left chiral field. The other half of the time, they will interact using a right chiral field. But the problem is the antineutrinos don't participate in this reaction here. They only participate in the reaction where a positron gets produced. And that reaction doesn't go because the nuclear physics will not allow for that, because this is an induced beta decay. It's not an induced anti-beta decay. So that means if the neutrinos are Dirac, we get a certain rate for this process here. If the neutrinos are Majorana, remember my cosmic neutrino background has the left-handed helicity component and the right-handed helicity component. As far as the left-handed helicity component is concerned, the story is the same as for the Dirac neutrino. That means that some of the time it'll go like a left chiral component, it'll produce an electron. The other half of the time it will behave like a right chiral component, and that doesn't know how to do this induced beta decay. However, there's also the right-handed helicity component of the cosmic neutrino background. That state will also speak either like a left chiral field or a right chiral field. And because the neutrinos are now Majorana fermions, the left chiral field is the one that knows how to produce electrons. Again, remember, the number of fields is less. So that means that there are only two, a left chiral field that knows how to produce electrons and a right chiral field that knows how to produce positrons. That's what makes the Majorana neutrinos different from the Dirac neutrinos. So at the end of the day, in the Dirac case, the neutrinos can, the left-handed helicity states can produce an electron. They give you a certain rate. In the Majorana case, the left-handed helicity states can produce an electron, but the right-handed helicity states can also produce an electron. And at the end of the day, you get twice as many hits as you would have gotten otherwise. So this means that if you could measure the cosmic neutrino background, deciding if the neutrinos are Majorana or Dirac is kind of trivial. You either have to count what the rate is, and if the rate is x, the neutrinos are Dirac. If the rate is 2 times x, then the neutrinos are Majorana. So it's a factor of 2 difference. It's very, very easy. Now, what are the problems with determining if the neutrinos are Majorana or Dirac in this way? The biggest problem, of course, is we have no idea how to detect the cosmic neutrino background. The rates for doing that are super tiny. It is exciting, however, that we do have a proposal that people have been exploring for a few years now that seems to be getting some traction and has made lots of promises that we might be able to see the cosmic neutrino background someday. There's something called the Ptolemy project. It has some complicated problems that people are working on, but somehow there's some excitement in the field that someday we might see the cosmic neutrino background. By the way, even if we saw the cosmic neutrino background, you can ask yourself that we actually never measured the neutrino cross-section. We measure the combination of flux and cross-section. So somehow, you can replace or you can exchange a neutrino versus Dirac by making your flux 2 times bigger or smaller. So you would confuse the two that way. So one question you're allowed to ask is, how well do we know the flux of this cosmic neutrino background? And the answer is, we know the number density on average ridiculously well. So that's not a problem. A different problem is we don't care about the average number density of the cosmic neutrino background, but we care about the density of the cosmic neutrino background here on Earth. And the question is, how well do we know that number? And according to some experts that I'm just going to quote, but I am skeptic, they will convince you that we probably know that number at the 10% level. So 10% level is not a factor of 2. That means that if we made this measurement, we would probably be in business. So that's kind of exciting. Okay, so that's one well-known source of a very, very low energy neutrinos. They're just out there, but we've never seen them before. So let's talk about something different, which is why don't we do electron photon scattering at low energies? And in particular, what would happen if I looked for E gamma goes to E nu nu bar? That's a weak process. The Feynman diagrams are here. And it turns out if I do this at very, very low energies, I can do the calculation and I can ask, what's my cross section? If I could measure this, the result is actually really, really amazing. This would be a great experiment because you can do lots of different things. And in particular, imagine that I have, let's say, an electron target and I'm shining a laser at it. And I'm looking at the recoil of the electron. I can certainly do this for many, many different photon energies. And in principle, my cross-section would look something like this figure on the left. And you can see that the cross-section is very exciting because you can produce the different neutrino mass eigenstates in pairs, but you can see the thresholds kicking in. So for example, the black solid curve here is what the cross-section would look like. And you can see that as the photon energy grows up, you start to see the different combinations of, let's say, nu1, or nu1, nu2, nu2, nu3, and so on and so forth. And the different contributions are here in different colors. The other thing that's highlighted here in this plot is there's a cross-section for the Majorana case, and there's a cross-section for the Dirac case. And already on the plot on the left, you can see that the dotted lines and the solid lines are different. And of course, you can plot the ratio of these things, and you'll notice that the Dirac cross-section can be much, much bigger, for example, than the Majorana cross-section, as you're scanning things as a function of the photon energy. There's an interesting point, which is as the photon energy gets bigger, again, you go into the regime where the neutrino energies are too big, so you can't distinguish Majorana from Dirac. And that's what happens once the photon energies go to about an electron volt or so. There's even some excitement here. You notice that the curve has this width to it. And that's what happens if you vary neutrino mixing parameters, including Majorana phases. So that means that this ratio of what you expect for the Dirac case versus the Majorana case depends on things like Majorana phases, for example. So this is very exciting. And the question is, why have you never heard about this? And the reason is because the rates are just ridiculously small. So if you didn't pay attention, there's some units here. And those units tell you that if you try to do this experiment with the baddest possible laser you can come up with and a gigantic electron target, you would get one event every age of the universe or so, which is bad. So it's not a good experiment for you to try to do. If you were very clever and you could come up with a target that's the size of the moon, for example, it would still not work because you have to worry about backgrounds. And of course, you're looking for E gamma goes to E neutrinos. And of course, the only thing you can measure are the electrons. And of course, you are at the mercy of elastic E gamma goes to E gamma scattering. And of course, you can say that I can see the gamma, so I'm not going to be fooled by this. But you can also look at things like E gamma goes to E plus 20 gammas. And then in that case, all of the photons are super soft. And you can say, oh, but that cross-section is super tiny, which is the correct statement. But even if you have a huge number of photons in the final state, the cross-section that you get will still be overwhelmingly much, much bigger than the one that we care about. So just to say, this is a great idea. It's a really, really stupid experiment. It would never work. But at least the idea is there. Here's another thing that also doesn't work. And we know that excited nuclei can undergo gamma radiation. So I have an excited nucleus, I can emit a gamma ray to de-excite. So I can do the same thing with a Z boson. I can start out with some excited nucleus, I can go to the ground state, and I emit an off-shell Z boson, and that Z boson can manifest itself as neutrinos. So that's an interesting idea. There's some nice papers about this. And I think the message here is that what you expect in terms of rates for Majorana versus Dirac neutrinos is also qualitatively different. It's off by some large amount, which is almost an order of magnitude on the one hand. On the other hand, the rates for these processes are just ridiculously small. By the way, for this particular kind of observable, you have to be creative to ask yourself, what is the observable? Because there's no gamma ray that you can see, but there are lots of ways that you can handle that. Okay, so the last topic I want to talk about for the last, let's say, 5 or 10 minutes is looking at neutrino decay. And I would say neutrino decay is an interesting process because in the standard model with massive neutrinos, the neutrinos must decay, at least the two heavier ones. And they have two well-defined decay modes. A neutrino can decay to a lighter neutrino plus a photon. And if you have enough phase space, a heavy neutrino can decay into 3 copies of the lighter neutrinos. So these decay modes, these decay processes are governed by the weak interactions, and they must happen. Now, the message I want to leave you with is that if the neutrinos are Dirac fermions or Majorana fermions, they will decay differently. And they decay differently in different ways. One way that turns out to be kind of boring is that if you knew everything about the neutrino mixing parameters and the neutrino masses, the partial widths for the decays would be different if the neutrinos are Majorana or Dirac. What I want to point out is that the kinematics of the decay is also different. Now, again, neutrino decay is fun to talk about, but it's also a very rare process because the width for that is very small, and it's proportional to the neutrino mass to some positive power. And if you plug in, regular numbers that we know about, the lifetime of the neutrino is expected to be many, 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 many times more than the age of the universe. Of course, if you have new physics, that can change dramatically because the bounds on the neutrino lifetime are not, 10 to the 40 years. They are very, very different. So it's an exciting thing to think about neutrino decay. And my job here is just to tell you how neutrino decay can distinguish Majorana from Dirac neutrinos. Now, I do want to say that if you were really excited about neutrino decay, life is hard not just because the lifetime is long, but you also have to worry about this neutrino going into neutrinos decay, and that usually makes it very difficult for experiments. But let's not worry about that because, again, we won't be talking about anything that you can observe in a real experiment. So the most interesting thing I'm going to tell you about is contained in this slide. And this talks about a neutrino decay. So the heavy neutrino goes into a lighter neutrino plus something. Imagine that something is like a photon. If I go to the reference frame of this neutrino, and if the neutrino is polarized, let's say it's polarized up, the photon comes out with a non-trivial angular distribution that's given by this expression that is over here. This alpha is some coefficient that depends on how much parity is violated in my theory. Again, in the weak interactions, parity is violated a lot. So this is how the neutrino will decay. If the neutrino is a Dirac fermion, if you have, let's say, a neutrino would spin up, the photon would come out with this distribution. If you have an anti-neutrino would spin up, and you ask, how does the photon come out of the decay distributions are actually related. One goes like 1 plus alpha cosine of theta. The other one goes like 1 minus alpha cosine of theta. And the only assumption you have to make here is that CP is conserved. Okay, so that means that when a neutrino decays, it decays with a 1 plus alpha cosine theta. When the anti-neutrino decays, it decays with 1 minus alpha cosine theta. This statement, it turns out, is also valid for Majorana neutrinos. Now, of course, if the neutrino is a Majorana fermion, the neutrino and the antineutrino are the same. So the only way that this statement here can be mathematically correct is if, in the case of neutrinos being Majorana particles, this alpha coefficient has to be exactly 0. Now, what the physics of this means is that if you have a Majorana fermion that's decaying into 2 other self-conjugate final state particles, the decay must be isotropic, independent of the interaction. So what this means is if you can see a neutrino decay and you measure the angular distribution of the decay, if the neutrino is Dirac, it doesn't have to be isotropic. If the neutrino is Majorana, it must be isotropic. This statement is not 100% true. It depends on CP violation. And it turns out that even if your theory violates CP a lot, it's the kind of CP violation that you normally talk about in things like B decays. So the process is a high order interference-like process. So the CP violating effects are super tiny. So it's not like even if you measure neutrino decay and CP was violated a lot, this would be still a great approximation. So that means that this is an exciting thing you can talk about, which means that if the neutrino is a Majorana fermion and it decays, the decay must be isotropic. If the neutrino is a Dirac fermion, the decay doesn't have to be isotropic. Now, the problem here is that you could be unlucky and you might have new physics that happens to have Dirac neutrinos and it happens to make the neutrino decay isotropic. And I don't know how to control for that. So that's one of the places where new physics can get in the way in a weird way by making the Dirac neutrinos decay just like the Majorana neutrinos. The Majorana neutrinos don't care about the new physics, but the new physics can screw up what the Dirac neutrinos are doing to fool you in some way. All right. So because I don't want to dwell on this too much, I do want to say that, again, observing neutrino decay is very hard. But it turns out that there is a scenario where thinking about these things is useful. And it's in the context of a neutral heavy lepton. As a lot of people know, looking for neutral heavy leptons is an interesting thing to do because it might have something to do with neutrino masses. It's a new particle that you can look for, et cetera, et cetera. And it is part of the programs of things like the LHC and Icarus and the Dune experiment and B factories and SHIP and Phaser New and all kinds of experiments are looking for neutral heavy leptons. So imagine that you actually discovered one. That would be super exciting. You would discover a new particle, you would celebrate, you might get a Nobel Prize. But after you've settled down, you would probably ask yourself, okay, so I've discovered a new particle. I'm calling that a neutral heavy lepton. Is that particle Majorana or Dirac? And getting the answer to that will depend on lots of different things. I would say the dominant way to get the answer to that will be to look for lepton number violation. And that's what, for example, people look for in a collider experiment. In a collider experiment, if the new neutrino state is a Majorana fermion, it can be produced together with an L plus, and it can either decay into an L minus or into an L plus in the final state. So you can tell that you have lepton number violation because you have some final states where lepton number was violated by 2 units. So that's an easy way to tell that you violated lepton number, which means that this new particle that you've produced has to be a Majorana fermion. Now, it's not guaranteed that your experiment that made the discovery of the HNL has the ability to do this. So you might be at a situation where, just like I was talking about before, you have to look for the kinematics of the decay of the new 4 into this two-body final state. And if you only have the weak interactions, in the weak interactions, I can calculate these alpha coefficients, and you will notice that all of them are not very much close to 0. That means that this thing that we were talking about of the angular distribution of the decay products of the heavy neutrino, they can reveal if the neutrino is Majorana or Dirac. Okay, so I'm running out of time. I want to say that we've been thinking about this for a long time, so we have lots of papers on this. We looked for things that include 3-body decays of the HNLs because the 2-body decays are rare. 3-body decays are more exciting. We looked for different ways of telling the two models apart. This is a very complicated kinematic space. I think the message from this figure is that the contour plots on the left and the ones on the right are different. One of those is Dirac fermion, the other one is a Majorana fermion. And the last thing I want to say, just a couple of words about, is A great place to look for neutral heavy leptons is E plus E minus collisions at the Z pole. Okay, so if you have a neutral heavy lepton that weighs about 10, 20, or 30 GeV, the best bounds on the existence of this particle actually come from LEP. So if you did a super LEP, you would probably be very sensitive to these particles living at this 10 to 20 to 30 GeV range. And that's something that people who talk about FCCE, they talk about this TerraZ program. And one of the things you can do with a TerraZ program is on top of a whole bunch of electric precision measurements, you can look for H&Ls. So I'm not going to talk about this very much because I've run out of time. But what's exciting about looking for for this particular process is if you wanted to tell if nu4 is Dirac or Majorana, you would not be able to do that by measuring the lepton number of the nu4, because the nu4 is recoiling against a neutrino, and you have no hope of deciding if that neutrino was a neutrino or an antineutrino. So you only can rely on kinematics. But what's exciting about this E plus E minus goes to new light, new heavy, is that not only is the decay kinematics of the nu4 different from Majorana or Dirac, but the production kinematics of the heavy Majorana nu4 or a heavy Dirac nu4 is also qualitatively different. And we have this really nice paper where we work out the details of how different these kinematic distributions are. And I'm going to skip this because I don't want to impose on your time more, but I want to come to the conclusions and maybe people can ask a question or two. So again, the message that I want to convey is that Majorana fermions and Dirac fermions are different things. They have different numbers of degrees of freedom. However, when you talk about massless fermions, you can't ask if a massless fermion is Majorana or Dirac. And because the neutrino masses are so small relative to the typical energy scales of your experiments, answering whether the neutrino is Majorana or Dirac is very, very hard. The way that we look for this traditionally is to identify something that Majorana fermions know how to do, that Dirac fermions don't, that Majorana neutrinos know how to do, that Dirac neutrinos don't know how to do, and that's to violate lepton number. So if you ever saw lepton number violation, you would be able to conclude, modulus some exotic things, that the neutrinos are Majorana fermion. On the other hand, you have another potential choice, which is to work with neutrinos that are not ultra high energy. And if you work with neutrinos that are not ultra high energies, the distinction between Majorana and Dirac stands out. You know, they really behave very differently. Even though you're not looking at an observable that's equal to 0, you have an observable that's not 0, but they just behave pretty differently from Majorana versus Dirac. The reason we don't talk about this too much, of course, is that the weak interactions are very unforgiving when it comes to trying to measure neutrinos at very low energies. So the rates are always super tiny. But on the other hand, if we ever learn or run into a new particle that happens to be a fermion and happens to be neutral, but also happens to not be very light, we might be asking ourselves, is that particle Majorana or Dirac? And maybe these kinds of observables will be useful. So I'm going to stop here. Thank you.
Thank you very much. We have time for questions. So if you're online, please just speak up because I don't see who is online. So maybe I start us off. Can you go back to that when you discussed the Z boson decay to the heavy neutrinos? So to what range of masses are you sensitive there? Or?
Yeah. So here's one example of an observable that you can compute. That's actually famous for E plus E minus machines. This is a forward-backward asymmetry between either the neutrinos or the antineutrinos if the neutrinos were Dirac. And you notice that the range of masses that we talk about are in some fraction of the Z mass. Mm-hmm. So that's the kind of masses that you care about. Of course, if you get too close to the Z mass, then the rates go to 0 because you run out of phase space.
Yes.
But if you've ever seen these constraints, which unfortunately I don't have handy, there's a very famous Delphi constraint that in the mixing parameter versus mass plane that is very deep and restricted to this tens of GeV kind of mass. Once the mass becomes too light, then the H and L is indistinguishable from neutrinos, so you can't see them.
Okay,
And once
because
the
they
mass
can
is too
become
heavy,
relativistic.
yeah, that's right. Everybody's ultra relativistic. Nobody decays. You see nothing, and they just look like a neutrino. They just, even if you have 20 sterile neutrinos, at the end of the day, if you sum up all of them, they sum up to 3 neutrinos, so that it doesn't violate the Delphi, the LEP result. So it's this, let's say, GeV to 75 GeV kind of range.
Okay, and it can, so the decay would be by the normal weak interactions, I
Yeah.
guess.
So the decays are variants of, it'll be things like this.
Yeah.
It will be things like this. And of course, as these things get heavier, the way you want to think about this is the dominant decay will be into either on-shell or off-shell W boson.
Mhm.
So this is kind of like a tau lepton. It decays into, it's a tau lepton if you flip the legs, right?
Yes. And to what kind of mixing angles are you sensitive to you
Oh,
get?
that's a
So
good,
in
that's a good,
comparison to neutrino mass, so if it could that
yeah,
that heavy neutral lepton contribute to neutrino mass?
yes. So as with all searches for heavy neutral leptons, I think the ultimate goal is to try to get close to these naive seesaw expectations, for example. And I would say that these kinds of searches are not there, but if you did have a Terra Z machine, you would kind of kiss the seesaw line for people who are kind of experts in this. So it's a nice place to look for your seesaw neutrinos because you're starting to be sensitive to naive expectations from just a regular type 1 seesaw.
Okay, now that's interesting because otherwise it would have to be pseudo Dirac, and then I guess you wash out.
Yeah.
And
So pseudo Dirac makes the story more exciting because somehow when the neutrinos are pseudo Dirac, everything that I'm talking about somehow has to vanish. So there's an interesting gain. So what happens is the following. When you start making your H&L pseudo Dirac, you can make your mixing parameter very large, but anything that will distinguish Dirac from Majorana also starts to go away. So that means that your observables that rely on the difference between Majorana versus Dirac, they start to be erased away. And that turns out to also be true in a very interesting way for what I'm talking about as well. And it's more subtle, so I don't want to talk about that. But you're completely right. Yeah.
yeah, no, thanks. Other questions?
I wanted to ask a question about Ptolemy.
Okay.
So what's the so I suppose it's not really a factor of two, really. I mean, depends on the mass hierarchy of what Ptolemy can do, even if you can do it. So my question was, what's the what's the sensitivity of Ptolemy to really detect a mass? So it depends, of course, on a variety of factors, but if you could really make a statement, at what level can you make a statement of whether it's accurate?
Yeah. So I assume you're talking about distinguishing Majorana from Dirac.
Yeah.
And I would say that the short answer is I don't remember, but one thing that you did point out correctly is that the size of the effect that we're talking about will depend on the neutrino mass ordering, because that will dictate to how many neutrinos, in quotes, is a Ptolemy sensitive to, and how many of those neutrinos are heavy, let's say. But once we know the neutrino mass ordering, this becomes a computable effect. So I think if we know the neutrino mass ordering, this will be known. We might have to know a little bit about the overall scale of the neutrino masses. So we have to know if the number of light neutrinos, if there's one massless state, or if all the states are relatively massive. But I think once we know all of that, calculating the distinguishability between Majorana and Dirac is completely calculable without any big uncertainties other than whether we understand the local flux of cosmic neutrinos where we are as opposed to the average flux. So if you believe in that calculation, then all of the numbers are under a lot of control, and we're still talking about an order one effect. So that means that if Ptolemy gets to see the cosmic neutrino background, if it got something like, let's say, 10 events, it will already be in a strong position to distinguish Majorana from Dirac because it's an order one effect.
That's a very strong position. Okay, yeah.
And people have done detailed estimates of this. So there's a Ptolemy paper from 2019 that talks a little bit in more detail about the quantitative aspects of this.
Okay, cool. All right, cool. Thank you.
Mm-hmm.
Yeah, I just had a question as well. You were talking about the neutrino decay, and you mentioned that the time scale will be cosmological. What sort of time are we talking? Is this sort of order Hubble or significantly longer than Hubble?
It's much longer.
Okay, so when you're talking about like the cosmic neutrino background, you don't need to take into account these effects.
You do not.
It's completely relevant. Okay, yeah.
It's an easy number to estimate. You can take if you want to get a bad estimate, you can take the muon lifetime and multiply it by the muon mass divided by the neutrino mass to the 5th power. So that gives you the neutrino lifetime. A very bad estimate, but it's a good enough estimate. It's really, really long. So, that's but again, I do want to emphasize that this is a standard model expectation for the neutrino lifetime. And you have to keep in mind, that G Fermi is quite small. And so if you do have new physics, the new physics can overwhelm the standard model contribution, and it can do that in a way that it makes the lifetime a lot shorter. So I think a better question to ask is, what are the experimental bounds on the neutrino lifetime? And those bounds, you can quickly bet, are not going to be 10 to the 30 years. They actually are a tricky thing to calculate. And I know that Yvonne's group has some very nice bounds on the neutrino to neutrino two-body final state. That is of order, I don't know, something many years, which I can't remember. But it's not, the age of the universe. It's something that's a lot less than the age of the universe. So between the
it's like 500 seconds, actually.
Thank you. Yeah,
but
thank
anyway.
you. Yeah. Sorry, yeah. So it's way less than I remembered. Yeah. So yeah, so let's say it's less than a year. So there's a lot of room between less than a year and 10 to the 30 years to look for new physics. Yeah.
That's very good. So I see that we are just past 12. So I would suggest